And the first day of lecture in statistics is really almost all vocabulary. All right, let's see here. I'm trying to, if people enter the Zoom call, I'm trying to make sure I get you counted present. So I'm doing 2 or 3 things at the same time. All right, let's share. You should be seeing my iPad. Get me out of the way. As I said, I didn't bring my Surface Pro home, which is what I normally use for lecture. So I'm using my iPad, which is perfectly fine. It works just fine. All right, so what are we going to talk about today? Today, we're going to start our introduction to statistics. And as I said in this first day, it's a lot of vocabulary. I do want to cover a couple of mathematical things at the beginning. I'm not sure how many of you have looked at the first homework assignment. Let's go in here and take a quick look. But the first homework assignment actually has quite a bit of review of rounding off percentages and scientific notation. So if you haven't looked at that homework yet, you are going to be doing a little bit of mathematical review. So I thought, well, maybe we should take a second and go look at that. Let's see, grades here. Looks like a couple of you've done it. All right. So what are we going to do? Get myself organized. So in chapter 1, we're going to talk about key terms. We're going to get a lot of definitions, which we need to be able to continue on in statistics. Now, it's been my experience teaching this for a number of years, and a student will come into my office and ask me for help on a question, and I'll say, how did you get the answer to number 1? Did you guess till you got it correct? And the answer is 99% of the time, why, yes, I did. So I would hope that that's not the approach you take. I would hope that the approach you take is to actually understand why that wordy problem has the answer that it does. So we're going to go over these key terms, and hopefully I'll remind you throughout the semester. The reason that's a statistic is bleh. The reason that's a parameter is bleh. So we'll talk about those terms. And then we'll talk about the sampling methods that we use to get data collection. And in between there, we're going to do a little bit on ethics, and I'm going to do about 2 seconds on ethics. There are several slides in the deck that cover ethics, but the one I chose this morning, and I was discussing it with my husband this morning, I said, I see these things posted on Twitter or Facebook or generally on the internet, and I think to myself, the one I'm showing is a friend of mine on Facebook, which I did not answer her, but I felt like answering her. Think, did you not pause and think about this before you posted? Because it's so silly, and it's a mathematical thing, but it's just posted with, as soon as people post math, it's got a ring of truth. And what she posted is just nonsense. It's pure and unadulterated nonsense. So if you can stop and think when you see this kind of stuff on Twitter or well, you guys probably don't do Facebook, but whatever, on TikTok, somebody posts something, it's 99% of the time probably their opinion, and they don't have any data to back it up. So we'll look at this screenshot she posted and say, where's her data to back this up? Okay. And then we'll talk about frequency tables. And actually, we're just going to really introduce frequency tables at the end of chapter 1. And then we'll get into actually creating frequency tables in chapter 2. So chapter 1 and 2 are butting up next to each other. And as a matter of fact, the last homework includes both the end of chapter 1 and chapter 2. They're combined. Okay, so what definitions are we going to get? We're going to talk about what are descriptive and inferential statistics. And we did talk about this briefly last Wednesday. What's the difference between descriptive and inferential? And then we'll talk about probability just in the context of defining what probability is. And then we'll actually get into finding probabilities later. We'll talk about what is a population and how does it compare to a sample. And when you use a number to describe something in a population, what you're using is what is called a parameter. So parameters, P, they deal with a population. And then when you're using a number, a value to describe something from a sample, that's a statistic. So P parameter, population parameter, S statistic, sample. So they go together. And then we'll talk about what variables are. And then throughout the semester, we'll say, okay, the variable is blah. We'll describe what that variable is. Okay, who's coming in? Now, there we go. I was admitting you, but wasn't seeing you. Yeah, you have to do this waiting room thing so that crazy people don't come into your meetings, which has happened. All right. And then we'll talk about data. All right, so the first part of your homework, first few problems, most of the problems in the first homework are review of simple mathematics. And I call this simple mathematics because this should be something you got in like the, I don't know, 5th grade, 4th grade, I don't know, really early on. But it's something you don't do very well. So that's one of the reasons why we have review problems in your first homework. And it's rounding. And rounding is very simple. If you're rounding to 1 decimal place, or you're rounding to the nearest integer, which is the first problem here, first question, you look at the number to the right of that. If that number is 5 or greater, you take the number that you're looking at it and you round it up. If that number is 4 or less, then you just leave it alone. You just truncate it. You take it off. So if we're going to round that number 2.38233 to the nearest integer, or in this case, it would be a whole number because it's positive, and the non-negative integers are whole numbers. The negatives, when you add those to the whole numbers, that's what makes them integers. So non-negative whole numbers are 0 and to the right. I don't know what I'm saying. So if I'm rounding this off to the nearest integer, I'm just going to round this off to 2 because I'm going to look at the number that's just to the right of the 2. It's a 3. That's 4 or less, so I just truncate it. So I just lop off everything to the right of the 2. So it's 2. Get my iPad here where I can actually write on it. And if I'm rounding off to 1 decimal place, well, 1 decimal place would be right there. So I'm rounding off that number. And again, I go 1 number to the right, which is 8, which is bigger than 5. So I take the 3 and I round it up. 2.4. And if I round to 2 decimal places, I can remember how to erase on my iPad. Here we go. And I'm not going to erase, too much work. If I round up to 2 decimal places, I'm going to round the 8 off. So I go to the right, it's a 2, so I just truncate 2.38. And if I'm going to round off to 3 decimal places, I'm going to round off the 2. I go to the right, it's a 3, so I just truncate 2.382. And if I round off to 4 decimal places, I'm going to round off to 3. I go 1 number to the right, that's a 3, so I just truncate. I get rid of that last 3. So it's 2.3823. And you do this very poorly. As a matter of fact, a few semesters ago, on the final, a student would have failed miserably if I hadn't given credit for round-off error. So just be really careful with your round-off error that you're rounding off properly. It's a small thing, but be careful. Typically, in my open math, in this course, they want you to round to 4 decimal places. That's just typically what they do. If they don't specify in the problem otherwise, that's probably what they're going to want, is at least 4 decimal places. Most problems early on, they tell you. And if you round it off to more decimal places than what they tell you, it's going to count it wrong. So just be really careful that you read the problem and you see how many decimal places they want you to round it off to, and then round it off appropriately. If they don't tell you how many decimal places to round off to, you're usually safe with 4. All right. Percentages. And this is one of my my daughter-in-law, who didn't go real far in mathematics in college, she said every human being on the planet should be able to do percentages. And she can do this kind of thing in her head. And so what she does to convert this to a percentage, she multiplies the top and bottom by 4 and then divides by 10. That's going to give you a denominator of 100. And that's what a percentage is. A percentage is a part of 100. That is what it is. So when you're talking about 30%, 30% means 30 parts out of 100. So that percent symbol always means out of 100, always means 1 over 100. That is what it means, or 0.01 if you want to use a decimal. So my daughter-in-law, she would do this. She'd multiply top and bottom by 4. And then to get it to be 100, she'd divide by 10. So 220 over 250 is 88%. 88 over 100 is 88 parts of 100, or 88%. Now, we're probably not as savvy as she is, or maybe we just don't think about it. So typically what we do is we actually do this division. So we take our calculator out. I'm not sure that I could do 220 divided by 250 in my head. I'm going to have to use some method to carry out that division. And I get 0.88. And to convert that to a percentage, to take a decimal and make it a percentage, we multiply by 100. And we go backwards if we're going the other direction. If we're taking a percentage and converting it to a fraction or a decimal, we divide by 100. So it's 88%, which we knew already. So to convert to a decimal, to a percentage, multiply by 100. To convert from a percentage back to a decimal, you're going to divide by 100. And this one is one that gets you all through the semester, because your calculator doesn't handle, well, it won't give you a very small or a very large number as a decimal. It's going to convert it to scientific notation. And this is exactly how your calculator displays it. So what this means is, what this E means is 10 to the whatever that number is to the right of it. So that's what it means, that E means exponent. Okay, so this is equivalent to 7.63 times 10 to the minus 4. That's what it means. Excuse me. So it's just a way of us writing a fairly small number in a more concise fashion. And it helps us from writing all those dadgum zeros. And it also helps us determine how many significant digits this particular number has, which we'll talk about later. We will review significant digits. So this has 3 significant digits because it has a 7, a 6, and a 3. Those are all significant. Now, if I write this as a decimal, what we do, this -4 tells me I need to move that decimal 4 places to the left. That's what it means. So this is a small number because its exponent's negative, so it's going to be a number less than 1. So this is point, and I always count. There are going to be 3 zeros, since that's a -4. There are going to be 3 zeros in front of the 7. 2, 3, 7, 6, 3. And we're good to go. So that small number in scientific notation, in decimals, it's 0.000763. So I don't know that that particular scientific notation is faster to write than that decimal, but sometimes when you get numbers like this, which we can get probabilities that are that small. It's way easier to write that in scientific notation. So how many zeros do I got here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7. Yeah, that's it. That is correct. So when you're doing a calculation on your calculator, make sure that you look to the right. And if there's an E there, then that means your calculators put your answer in scientific notation. And you're probably going to have to put it in MyMathLab in scientific notation. If they want a decimal, then you're going to have to convert that scientific notation to a decimal. All right, let's get into our definitions now that we did that quick review. What is statistics? And we're going to repeat this definition here in just a few slides. What is statistics? It's the science of collecting, organizing, analyzing, and interpreting data in order to make decisions. And I used to say this all the time, and I still think it's true. There's really not any point of taking data, collecting data, unless you have a purpose for it. There's some kind of decision you need to make. And so often we're just analyzing data to analyze it. What's the purpose of that? And that's really happens in these retrospective studies that we're going to talk about in a few minutes, where you have data that's already collected and then we try to make it fit a scenario that we're interested in. And that's not the way we do things. The way we do things is we have a problem or we have an interest. We take data, we analyze the data, and then we make a decision based on the data that we analyzed. So the goal of this is not to perform a lot of calculations, because believe you me, your TI-84 calculator does this amazingly well, as does Excel. Excel does this very well. So you have tools readily available to you that will actually do the calculations. What's important is that you understand why you're doing that calculation. And that's one of the things, there are things that frustrate us as professors, but one of the things that kind of frustrates us is that we want the understanding to be there and you're trying to get a grade. I mean, that's the reality of the situation. You want to get a good grade, so you'll guess until you get the right answer. If you do that, then take my advice once you guess the correct answer, because gosh, I've never done this. Once you've got the correct answer guessed, figure out why it's the right answer. Just pause and ponder that for a minute. All right, so the first kind of statistics that we're going to discuss in this course are descriptive statistics. And these are numbers that describe your data. And there are a lot of different ways you can take the data and use it to describe your population. And certainly one of those ways is a graph. And we've got two different graphs here. And graphs are wonderful because just looking at them, I can immediately see information. Like looking at that pie chart on the left, I immediately see that the yellow pie is the big pie, big piece of the pie. So what does that represent? Well, then I can go over to the legend and I can see, oh, that's freshmen. So the classification of statistics students, the vast majority of them are freshmen. So you can see that immediately from the pie chart. I don't know the exact numbers, but I could certainly ask the researcher, well, what's your data? Can I see your raw data? And they can tell me how many statistics students are actually classified as freshmen. The first chart is a bar chart, and bar charts are very helpful to show us a comparison between two different categories. And it gives us a frequency. It gives us how many are in that category, either by raw number. It really is 12,000, whatever it is. I'd have to put my glasses on to see that. So that first college, the number of part-time students is 13,296. So they actually put the label on top of the bar. So I immediately know exactly how many students are part-time at that college. The other way you could do it, you could write that as a percentage, which we just looked at percentages. You could take that 13,296 and divide it by the total, and you could write that as percentage. It would take that vertical axis and change it to percentages. And we call that relative frequency. And we do that all the time. All the time. So you could present that bar chart either way, but you can see just by glancing at it without even looking at the numbers that there are more part-time students at both colleges. And at the second college, there's significantly, well, I use the word significantly, which I should not use unless I'm sure that it's significant, but it looks like quite a few more are part-time at that particular college. And maybe it's a two-year college and the other's a four-year college, because that is going to happen, correct? Two-year colleges are going to have more part-time students, typically. Okay, so how can we summarize data when we're trying to describe a population? Certainly, graphs are a great way of doing it. That's first slide there. They're typically the first way you describe your data, but you can also use numbers, and we will actually calculate these later. Some numbers that we can use, which we already did on last Wednesday if you were in class, and we did the sleep dot plot. Someone in the back, and I don't remember who you were, I'm sorry, you calculated the average. So the average is one way of us describing our population. We're going to use other numbers, median, mode. We're going to use standard deviation, variation. We'll use other numbers just to use to describe our population later. Now that's descriptive statistics. What's inferential statistics? Now this is just one example of inferential statistics, and I'll talk about this example here in just a second. But after we've studied probability and distributions, we're going to use formal methods for drawing conclusions from our good data. So we can say, I'm 90% confident that the population mean is between these two numbers. And that might be important for us to be able to say, because one of the videos we're going to watch later actually talks about battery life. And the company has to be able to tell customers that we're 95% confident your battery is going to last between 10 and 12 hours, whatever the value is. So you know from that, there's an inference that every battery I buy from that company is going, with a 95% confidence, is going to last that long. That's an important thing to be able to tell your customers. Now, this example here is a regression line. And this is something that you do quite a bit in science. Any of you are going to take chemistry or physics. You're going to take data, and one variable in your data set is going to be related to the other variable. And that's what we have here. So we have a set of data that contains two values that are somehow related to each other. And since they're related to each other, we can plot those on a coordinate plane. And once we have the data plotted, that's the blue dots, that's our actual data that we collected. We can see, just looking at the scattering of our data plots, that looks fairly linear. It looks like it could be a line. So we can use our calculators or Excel. It's very, very simple calculation to do. It's just a few keystrokes to find the equation, the linear equation that fits that data the best. It's called the regression line. And then we can use that equation of that line to do some predicting. So if I don't have a data value for like 20, I could actually predict what the Y value is for that X value of 20 if I'm interested in finding that out, which I may be. And certainly we're only going to talk about linear regression in this course, but there are certainly other regressions that you could look at, such as exponential or logarithmic. Does my data fit that kind of model instead of a linear model? For time, we're only going to look at linear models, and we'll look at those in chapter 12. So again, what's the goal of statistics? It's not just to perform the calculations, although certainly you have to do that because you have to get an answer that you type into my OpenMath. But hopefully to get an understanding of why you're getting that answer and why is that answer important? What does it mean? And again, I highly encourage you on those multiple choice. I feel like I should take all the multiple choice out. Man, then I'd have to grade a lot. But anytime that you guess until you get the multiple choice correct, which you can do, I know, stop and ponder why the one you guessed is correct. All right. And it says, if you thoroughly grasp the basics of statistics, you're more confident in decisions you make in life. I think that's true. I think that it really helps us to, and it helps you discern the information that oh my goodness gracious. And those of you who've had me before, you've heard this before. See my phone? The best thing that ever happened to civilization, the worst thing that ever happened to civilization. It's a conundrum because it's both. We have information at our fingertips, and I don't know about you, if you ever unplug, like we go on cruises typically every year or so. And when you unplug on a cruise, because we don't typically pay for internet because it costs too much, you get kind of crazy at the beginning. It's kind of go, because you think, oh, I can just look that up on the internet. Oh, no, I can't. So it's a wonderful thing. It's also a terrible thing. And it's a terrible thing because so many people put stuff out there that just it's not true, which we'll look at in a minute. So just be careful, and hopefully statistics will help you to at least say, I'm going to question that. I'm going to ponder that. And then this morning, when I was pondering the slide I'm going to put up in a little bit, I Googled it, and there is no evidence whatsoever anywhere that this is true. As a matter of fact, it took me about 2 seconds to get evidence to show it wasn't true. All right. What's probability? Probability is the chance that something happens. So it's the mathematical tool that we use to study randomness. And we think the universe is fairly random, But maybe it's not. There are a lot of things in the universe that are fairly predictable, and we can predict those using probability. We can predict the probability of me getting a 1 if I roll a single fair die, and we talked about that on Wednesday. So I can predict that. I can predict the probability. Now, there's this thing called the theory of large numbers that says if I flip a coin once, flip it twice. We need to flip it 2 times. The probability of me getting a head and a tail theoretically is a half if the coin is fair. So if I flip it, I got a 50-50 chance of getting a head or a tail. Now, if I flip it twice, if I flip it 4 times, what's the actual reality, the result of that experiment? Do I get exactly on 4 flips, 2 heads and 2 tails? And the answer is probably not, because you need to conduct the experiment a large number of times to see the theoretical probability. The theoretical probability, again, if you got a fair coin, got a head and a tail, the theoretical probability is I flip it, I get a head or a tail, 50-50 chance. But the reality of that situation is probably not going to get exactly 2 heads and 2 tails on 4 flips of a coin. Now, if I flipped it 4,000 times, then we get closer to what the theoretical probability is, 2,000 heads and 2,000 tails. Statistics is based on the theory of probability. It started with games of chance. That's mathematics is, I think about 99% of mathematics is fairly practical. There are theoretical mathematicians out there, and they're way smarter than me. But most of the time, mathematics, it's whatever was developed was because there was a need practically for it. So statistics is one of those things that there was a practical need for. What's the chance of me winning this game? Am I going to play if the chance of me winning? Well, sometimes we do. Like buying a lotto ticket. The chances of you winning the lottery are slim and none, but we buy one anyway. It's fun. But that's the reason statistics probability was developed. Predictions take the form of probabilities, the likelihood of an earthquake, of rain, of ice. Yesterday, they were giving us a 70% chance of precipitation, which simply means that on any given day, under the same conditions, 70% of the time they got precipitation. So they look at the preceding data and they can see that all the conditions of the atmosphere, etc., on those days, 70% of the time we get precipitation. So that's what those predictions mean. What's the likelihood that you get an A in this course? Very good, I'm sure. We use probability to determine the chance a vaccine works. Stockbrokers use them for investments, whether you buy a lotto ticket or not. So your study of statistics, you use the power of mathematics, probability, calculations to analyze and interpret your data. Okay, key terms, population. A population is just anything you want to study, whatever that may be. And the example I always give is all the students at Redlands Community College in the spring 2024 semester. So if I'm interested in that group, that's my population. So it's any collection of people, things, objects that you want to study. All right, so let's define what a population, let's see if we can figure out what a population is. So we're going to use this example here for the next few slides. So we have a college, and we are interested in knowing the average amount of money first-year college students spend on school supplies that do not include books. So anything that you spend that's not technically a textbook, or in your case, you don't have any textbooks in this class, but whatever other textbooks you have, anything else you have to spend, pencils, pens, paper, notebooks, etc. So we randomly survey 100 first-year students at this college, and we have that 3 of those students spend $150, $200, and $225 respectively at their school on supplies that do not include books. So what's your population? Who are you looking at? Anybody want to venture a guess? Type it in chat.
The students.
The population is the first year college students. That is what thank you, Jake. I think that's who said that. That's who we're interested in looking at. So our population is the first year students attending this college. All right. Good job. Sample. To study a population, we select a sample. And every time I teach statistics, either we've had an election or an election's coming up because they campaign forever. So it's always an election going on. We have an election coming up. Have you heard that? So why do we take samples? Because typically, to look at an entire population is not practical. So we take what we hope is a representative sample of our population, and we use that sample to gain understanding and information about the population. So if you think about the election that's coming up in November, the number of people who are registered to vote in the United States, that's a huge number, hundreds of millions of people. So if we want to survey, or we want an idea who's going to vote for whom, which they are doing right now, they're already polling, got 900 million different polls that are all polling people to figure out who's going to vote for whom. It's just impractical for them to survey hundreds of millions of people. It couldn't happen. It would take you longer than the election would be way over before you surveyed all of them. So they pick a representative sample of the voters who are likely to vote to get an idea of who's going to vote for who. So samples are representative portions of the population. All right, so what's your sample here? So our population is the first year college students at this college. What's our sample?
The 100
What was that?
the 100 first year students.
The 100 first year students. Thank you, Dusty. So out of that population of these first year college students, we took a sample of 100. And those 100 we're going to use to represent our population. And who knows? I mean, if this is a huge college, there could be 20,000 students in the freshman class. So we're not going to survey all those. Okay, what's a parameter? A parameter is a value that comes from the population. So if we were to look at the entire population of students at Redlands Community College in the spring 2024 semester, and we were to count the number of students that have blue eyes, that frequency of blue eyes would be a parameter, because we're looking at every single solitary student. That's not, as we talked about, this probably not practical, although in our particular case, the freshman class or the entire student body at Redlands is not humongous, so we might be able to do it, but it's still large enough that it probably makes sense to take a sample. Okay, so what's your parameter here? We want to know the average mean amount of money spent by first-year college students at this college on school supplies that do not include books. So what is the parameter we're interested in? the mean amount of money spent from all the students. So the mean amount of money that our population spends. So the parameter is the average mean amount of money spent excluding books on by first year college students. So it's the mean of all the students. Okay, what's a statistic? A statistic is a number, a value that describes a property of the sample. So, for example, we could consider the class of elementary statistics that meets at 8 a.m. Monday and Wednesday mornings to be a sample of the population of all students at Redlands Community College in the spring 2024 semester. And I could count the number of you that have blue eyes. And that could be a representative of my population. Then you may actually be a fairly good sample for that particular attribute. So what's your statistic? So the parameter is the average of all the students. What's the statistic you're going to calculate?
How much was spent
By whom?
by those 100 first-year students?
There you go. So if we calculate the average of our sample, the 100 first-year students, then we would be calculating a statistic. Okay, variables. Variables are what variables are in all of mathematics. Variables are values that can vary. That is what they are. In statistics, we use capital letters. I don't know why. I haven't Googled it, but that's what we do. And typically we use capital X, and it represents the characteristic of interest. So capital X in this case, and I guess we need to talk a little bit more. They can be numerical or categorical. So they can actually be a number value, or they can be attributes. So we could measure the height of students in the 8 o'clock statistics class. That would be a numerical variable. I'm interested in heights, or I'm interested in eye color. So that would be an attribute. So I would just check what color everybody's eyes are: blue, brown, gray, hazel, etc. So they can be numerical, categorical, but it's the thing I'm interested in. What else do we need to say on this one? So for example, if I let X be, capital X be the height of students in the 8 o'clock statistics class, then little x, smaller case value X, would be the values that I assign to that capital letter X. So if I measured you and you measured 52 inches, then one of my little x's, one of my data values would be 52 inches. That is a data value that corresponds to that variable, the height of students in the elementary statistics class. It can be like a party affiliation. Did you hear we have an election coming up? So it could be an attribute like Democrat or Republican. That would be categorical. And with numerical values, we can do calculations. Categorical, we really can't. As soon as you start counting categorical data, then you've turned it into numerical data. So just the student has blue eyes. That's categorical. As soon as I count the number of you that have blue eyes, I've changed that to numerical data. Okay, so what's your variable? Well, it's the attribute you're interested in looking at. What was the attribute that we were interested in looking at? How much money first-year college students spend on supplies other than books? So typically the way that we write this is we say capital X is equal to, and then describe what the variable represents. So capital X is the amount of money spent excluding books by first year college students at San Jacinto College, which I can never say. And I apologize. I mispronounce things. All right, data. Data is the values you actually collect. So what's your data here? Now, I assume I collected 100 pieces of data, but what have I only got represented here? 3? So I've got 3 pieces of the 100 values that I collected. And so the data values that I actually see are the actual amounts that are spent, the 150, the 200, and the 225. So that's the actual data. So if we let capital X be the amount spent, so this is typically the way we do this. We let X be the amount spent, which I can't write this way. Then little x would take on the values 150, 200, 225, etc. I don't know what the other 97 values are, but that's typically the way we write this. Okay, what's an experiment? So we're going to talk about what an experiment is. We're going to talk about 3 types of studies, and then we'll talk about a controlled experiment, and then we'll discuss ethics briefly. What's an experiment? So does aspirin reduce the risk of heart attacks? This is an experiment they've done several times, and I keep hearing conflicting results from these experiments. I need to go Google what the latest results is. And that's one of the things that kind of irritates you as a statistician, is they'll come out with a study saying, yes. And they'll come out with a study, well, maybe not. Is one brand of fertilizer more effective at growing roses than another? Something you could certainly conduct an experiment to find out. Is fatigue as dangerous to a driver as the influence of alcohol? I've seen that they've done studies on that. Questions like these can be answered if we use truly randomized experiments. And we're going to look at some of the important aspects of experimental design. And proper design ensures that you're going to get reliable, accurate data, which is why a researcher should always be willing to share their data with other statisticians, always. If they won't share your data, ignore the study, hands down, because you want people to validate your results. You want to know that what you found is actually the truth. That's the ethical way of doing it. So the purpose of an experiment is to investigate the relationship between 2 variables. When one variable causes a change in another, we call the first variable the explanatory variable. So it's the one that we adjust the values to. And then we look at what the effect is on the other variable, and it's called the response. And that should make sense that it's the response variable, because it's responding to what you did with the explanatory variable. In a randomized experiment, the researcher manipulates the values of the explanatory variable and then measures the results in the change in the response variable. And the different values of the explanatory variables are called treatments. And an experimental unit is a single object or individual to be measured. So you want to, for example, investigate the effectiveness of vitamin E. And this is a study that's certainly been done and kind of been debunked since it first was done many, many years ago. So you recruit a group of subjects, you give some of them vitamin E, the other ones you don't. and then you see that there's a difference. So does that prove that vitamin E makes somebody healthier? And the answer is not necessarily, because that's one of the problems with an experiment. You really do have to control all the factors in your two groups except the treatment. The only difference in the two groups is the treatment they're receiving. If that's the only difference, and the group that takes vitamin E is significantly healthier than, well, I keep using the word significant, we'll talk about that later, is healthier than the other group that didn't receive the vitamin E, all other factors controlled, then you can make that conclusion. But frequently, what we do is exactly the opposite. We don't control all the variables besides just the treatment taking vitamin E. Those are called lurking variables, those other things that affect the response variables. Any explanatory variables that are affecting things that you're not controlling, those are lurking variables. I think I've talked about most of those. Yeah, I've said that on the previous slide. Okay, so the types of studies that can be done, a retrospective study, this is done all the time because the data already exists. So the data that was taken, can we look at it in context of another area of interest? And sure, we could do that. So any data that's already been taken that you're examining again, that's a retrospective study. An observational study is we just observe the participants in the study and we don't actually do anything to them. So we don't apply a treatment, we just observe. And an experiment is where we actually apply a treatment and then measure the responses of those treatments or that treatment. And I've actually had students do observational studies before in honors, if you're ever interested in taking this for honors. Things like observing what hand they use, what's their dominant hand. That's just something you can observe and count. A controlled experiment, when the participation in a study prompts a physical response from a participant, it's difficult to isolate the effects of the explanatory variable, and that's putting it very mildly. Number of years ago, I was working at Seagate, and we had a group, environmental health and safety, that created a bunch of courses in I can't remember the name of the product they were using. But anyway, the student would be taking the course online and they would receive, we called it the black screen of death. And they would just, going through the pages, they'd get this black screen. And then the course was done. They could not take it again, could not relaunch it. It was done. Whatever happened, they couldn't even go to another computer. So it was something being stored in the database of our learning management system that stopped the students from ever taking the course again. And we had a huge study at the company conducted by a Six Sigma expert to try to figure out why this was happening to random students in different locations in the world, different computers. And they finally isolated it to some setting on the computer, and it wrote some information to the database where it told the student they could never take it again. It was the weirdest thing ever, but to be able to figure that out took about a year of controlled experiment where we would put the user on different computer. It was a big deal. But anyway, to be able to get rid of all the lurking variables that could be affecting this, to isolate to the one or two variables that was causing the issue, was a big production, believe you me. Okay, so when we're talking about people and you're conducting an experiment, one of the things we do to counter the power of suggestion, and I know there's a new study out about the placebo effect that I need to read, because they're saying it's not as prevalent as researchers once thought it was, the placebo effect. But that's what we do, is we create a control group that we give a placebo to. It's actually not a treatment that does anything. So each group thinks they're getting the medication, but one is receiving a placebo. So it it takes care of this. If I'm receiving a placebo, but I'm getting better, then that's probably not the medication, because you're not receiving the medication. That is a placebo effect. Blinding, we use blinding so that a person who's involved in the research doesn't know whether they're receiving the active treatment or the placebo, and that mitigates that effect. So they're getting a pill, but they don't know if it's the actual medication or not. A double-blind study means that the person receiving the treatment doesn't know that they're receiving the treatment or a placebo. Neither does the researchers. So they use codes and things like that so the researcher doesn't actually know what the person is receiving. And then later, after the treatment has been studied, then they go back and see whether or not that patient actually received the treatment or not. Was it a placebo, or was it the treatment? So they don't even know when the study is occurring, which really helps control the experiment. Okay, ethics. So here it is. This is what my friend posted on Facebook. And it's not really statistics, but it's one of those, again, I said at the beginning of the class that when we post something that's got numbers in it, everybody goes, oh. Right. My wife, and this is apparently a screenshot from the official Dana Dargos account, which I don't know if that's supposed to be on Twitter or where that's at, but I couldn't find this person on Facebook with that account name. So maybe it's a Twitter. I don't know. I couldn't find any evidence that this actually is a real post. My wife and I left graduate school 23 years ago with a combined total of $70,000 debt. Since then, we've made $500 a month payments for 23 years, which is $138,000 if you're interested. We still owe $60,000. And then, it's political. Explain to me again why student loan debt shouldn't be canceled. So my first question, I was going to type in the Facebook and I slapped my hands. What, they go to a loan shark? Who did they go to for this loan? Are you kidding me? No way, no how. Can't be. There's no way if you pay $500 a month for 23 years, what's your interest rate? Is this a credit card? Did you put this debt on a credit card? No way. No way. And you can just do some. Why would you take out a loan that's got a student loan with a 23-year payment? Is that because you want your payments to be low? I suppose. But what kind of interest rate are you paying? It's the whole thing is kind of sketchy. And the truth of the matter is, it took me 2 seconds to go online and find a student loan schedule. How long did this take me to do? 2 seconds. And this is with a 10% interest, which is really high for student loans. I'm not sure what they are. What are they at? 4%, 5%? I don't know what they are these days. When I got my student loan eons ago, I need to talk to my daughter about it, because she actually has active student loans, because she went to graduate school and that's how she got her degree, and her graduate degree was student loans. But what you can see here, I'll put my glasses on, this schedule, this is 10% interest on a 30-year payback of $70,000. And when do they owe $60,000? They still owe $60,000 in principal at about year 9. right there. And then what happens? It's just like any amortization loan. You pay the interest up front and eventually start paying off the principal. It's just like a house. If you buy a house, you pay the interest up front. And then after about 20 years, you actually start putting a pretty good dent in the principal. But after 23 years, if I'm correct here, after 23 years, they're still owing, 30-something thousand dollars. That's true. But it isn't 60. So it didn't take me a long time. And this is a 30-year loan at 23 years. I can't imagine taking out a student loan for 20, 30 years. That's most people try to pay them off. When I had my student loan eons ago, I tried to pay more every month than my payment. Because when you're young and you're making money and you don't have any kids, you take out the loan like that. Well, that's exactly what it was. I was working, I'm making good money, had an engineering degree, didn't have any kids, wasn't married, so I paid my loan off. But that's all neither here nor there. It's just that when you see that kind of thing on the internet, pause and ponder it and think, can I actually figure out if that's true or not? And it usually doesn't take a lot of effort to figure out if it's true or not. So just be careful when you see stuff on the internet. All right. Go back to my PowerPoint. And then I'll let you go through the other ethical things. There have been quite a few things coming out in the last few years about researchers that just out and out falsified data, just out and out made it up. And then use the excuse, well, I really wanted to make a point. I wanted to emphasize this. So they just make up their data? No, you can't do that. The data is what the data is. It takes you where it takes you. It represents what it represents. It's not, never go into a research study trying to make a point, to try to prove something. That's not the point of this. It's you're interested in it, doesn't make a difference. And let's find out if it does. And if it doesn't, it doesn't. You've done a good thing. Even if it doesn't prove the point that you're interested in, you've still done a good thing. Honesty and ethics is what it's important here. And there is a quote, and I went out online to try to who to attribute this quote to. And it comes from Mark Twain, but he said it came from somebody else. I think he said Disraeli. It's, there are lies, there are damned lies, and they're statistics. So don't be in that category. Statistics can be a science for good, a mathematical science that proves good things, or it shouldn't prove good things. It just be what it is. Your data is what your data is. All right. Okay, so researchers want to investigate whether taking an aspirin reduces the risk of heart attack. 400 men between the ages of 50 and 84 are recruited as participants. The men are divided randomly into two groups. One group will take the aspirin, and the other group will take a placebo. Each man takes one pill each day for 3 years, but he does not know whether he's taking aspirin or the placebo. At the end of the study, researchers count the number of men in each group who have had a heart attack. So let's identify the following values for the study. What's the population? What's the sample? What's the experimental units? What's the explanatory variable? What's the response variable? And what's the treatment? Okay, so what's the population? Well, who are we interested in? Are we interested in men between 50 and 84? So the population of this study, that the group that we're interested in, are men between the ages of 50 and 84. What's the sample? Well, from the again, not reasonable to look at the entire population of men from the ages of 50 to 84. So we look at a sample of what, 400? So we'll look at 400 different men to represent the population of men between 50 and 84. What are the experimental units? Well, it's those poor slobs that we're giving the aspirin or the placebo to. So the experimental units are the men in the study. Okay, what else do we have? Explanatory variable. What's the explanatory variable? Well, it's the medication that we're giving them, either the aspirin or the placebo, because both of those are the treatments that we're giving to the men. Okay. What's the response variable? Whether they have a heart attack or not, right? And then the treatment is the placebo or the medication. All right. Okay, I did want to talk, how much time do I have? 8 minutes. Just ever so briefly about qualitative, quantitative, discrete, and continuous, because you have, the homework is weird and I need to fix it, but I haven't yet. I inherited this class and I have yet to fix the homework because there are problems in the 1.4 that are more likely 1.2 questions. So that's what we're going to talk about. Okay, there are two types of data that you can take, qualitative and quantitative, and we've already talked about this. Qualitative data is categorical, it's a description, some attribute, and quantitative is a number. Quantitative data are always numbers. Again, as soon as I start counting something, a category, as soon as I start counting it, it becomes quantitative data. So I can say students in the class have either blonde hair, brown hair, green hair, blue hair, I don't know. But as soon as I say I have 5 students in class that have blonde hair, I've counted it and I've made that categorical data quantitative. Quantitative data are the result of counting or measuring, one or the other. The amount of money, pulse rate, weight, number of people living in your house, whatever. So quantitative data can either be discrete or continuous. What makes it discrete or continuous? If you count it, it's discrete. If you count it, it's discrete. If you measure it, it's continuous. Count it, discrete. Measure it, continuous. And if you think about a tape measure, if you think about that for a second, and you think about measuring something with a tape measure, can you ever be completely accurate in your measurement? And the answer is probably not, because you're always going to get to the nearest whatever. So it's continuous because you're never quite at that exact value when you're measuring it with a tape measure. That's the way I think about it. So if you measure it, it's continuous. If you count it, it's discrete. So who carries books in their backpack anymore? Does anybody do that? But if you were to count the number of books in your, maybe notebooks, the number of notebooks in your backpack, if you count it, that's discrete. If we put it on a scale and we measure the weight of the notebooks you have in your backpack, then that's continuous. If I count it, discrete. If I measure it, continuous. Okay, so let's just do a quick example here. You go to the supermarket, you buy 3 cans of soup, and they give you the number of ounces in each can of soup, 2 packages of nuts, you have walnuts and peanuts, 4 different kinds of vegetables, broccoli, cauliflower, spinach, and carrots, and 2 desserts, Cherry Garcia ice cream and chocolate chip cookies. Name the data sets that are quantitative, discrete, quantitative, continuous, and qualitative. Well, what could be the qualitative data? The type of soup you have tomato bisque, lentil, and Italian wedding. You've got different kinds of nuts, walnuts and peanuts. Those would be the qualitative. Those are the attributes of the things that you bought at the store. What are your quantitative discrete? Well, you have 3 cans of soup. 1, 2, 3. You count those. You have 2 kinds of nuts, peanuts and walnuts. So the data that you count, that's quantitative discrete. What's quantitative continuous? Well, they give us the number of ounces in the soup. So 14.1 ounces, that's a measure of how much soup you have. It's a measure. Since it's a measure, it's continuous. You get 16 ounces of Cherry Garcia ice cream and 32 ounces of chocolate chip cookies. Again, that's a measure of how much that thing you have. So since it's a measure, it's continuous. So discrete, got 3 cans of soup. Continuous, I got soup that weighs 14.1 ounces, etc. Okay, we'll do this and then we'll call it a day. We got 2 minutes. What kind of data is this? Is it discrete, continuous, quantitative, or is it qualitative? So the number, and it gives you a hint, by the way, hint. Data that are discrete they often start with the words the number of. So the number of pairs of shoes you own. Number, it's quantitative because it's a number, and it's discrete, right? Because you would count. You'd go in your closet. Don't go into my closet. I don't want to know how many pairs of. Once upon a time in my life, I had 1 pair of shoes. That's it. 1 pair, 1 pair. Life has changed. I have way more than 1 pair of shoes. Okay. The type of car you drive. Well, that's obviously an attribute. So that's qualitative data. The distance. Okay. Now this can get tricky. If you measure the distance from your home to wherever you're going on your trip odometer, it's a measure, then you could say that's quantitative continuous. If you just, say, okay, like where I live, okay, it's a 1/4 mile, maybe it's a mile to Foreman, it's a mile to whatever, so if I just count the miles, then I could say that's discrete quantitative. The number of classes you take, the number of, that would be discrete quantitative. The type of calculator you use, that's quality, that's an attribute, that's going to be qualitative. The weights of sumo wrestlers, you're going to put them on a scale and measure their weight, that's going to be continuous quantitative data. The number of correct answers on a quiz, that would be discrete because you're counting the number that you got correct. And then IQ scores. IQ scores are measured, so I would argue they're continuous, quantitative, but they're stated as a discrete number. So they give you some kind of test and they measure your IQ, but then they state it, well, your IQ is 110 or 120 or whatever it does. So they state it as a whole number, but they actually measure it. So, is it discrete? I don't think so, because I don't think they count how smart you are. They measure, and excuse me, IQ is not a measure of how smart you are. Well, that's a whole different discussion. But they measure it. So in my argument would be that it's continuous. And I'm right on time. Are there any questions? I have a survey to ask you. I'm going to ask you something. I'm going to stop my recording.